For the worksheet that I gave you, we're going to later need some values of sine and cosine. So what is the value of cosine of pi over 4? Yeah, something like this, 1 over square root of 2. You can write that again like that. And sine of pi over 4? The same. Cosine of pi over 2? 0, and this is 1, right? Okay, great. We've gone through several examples here. Today we're going to cover these two numerical algorithms that use divide and conquer. We're going to do a matrix multiplication algorithm that's faster than the simple algorithm that you're accustomed to. And then we're going to talk about the fast Fourier transform, which is a really important algorithm for all sorts of signal processing, but also for multiplication, for pattern matching. It has applications everywhere. And then on Tuesday, we're going to talk about the last example of divide and conquer, which is a median finding algorithm that I think you referred to a few days ago. That's just an outline. So today, let's go through this matrix multiplication in FFT. So I hope that everybody was able to complete this matrix multiplication primer. The number right here is essentially 1 times 5 plus 2 times 7, right? So it's 5 plus 14 is equal to 19, right? So that's an example of what the matrix should be. In general, if you have an n by n matrix here, and you're multiplying it by another n by n matrix, your result will be n by n, and each value right here is going to be the result of multiplying, so Cij, right, is going to be the sum of multiplying Aik times Bkj. How many multiplications does it take to compute this summation? Takes n. So matrix multiplication, it's going to be n squared terms, each of which takes n operations. The standard schoolbook algorithm for matrix multiplication will be n cubed. That you would basically loop over all of the positions of this matrix and compute each position using the row column dot product. We're going to study divide and conquer method for this, and in office hours, I noticed that many of you are still not taking the approach, the algorithmic approach to solving the homework. So many of you are using intuition and ad hoc approaches. You're saying, I know that there's some recursion, so I'll divide into 2, and divide into 2, and divide into 2, and divide into 2, and come all the way to the base case, and then recurse back up, and so forth. What I really want you to focus on is the way that I'm presenting how we do these, how we do merge, how we did Karatsuba, how we did closest pair, how we did arbitrage. So with matrix multiplication, the way I would approach this in a divide and conquer would be, let me take my input matrix, which is n by n, and let me divide it into a similar problem that is exactly the same form. So in particular, as a first approach, let me try to divide these matrices into 4 matrices that are n over 2 by n over 2. If we were to do that, no matter how big our matrix started, we would end up with a problem like this, A, B, C, D times E, F, G, H. And our resulting product would just be AE plus BG over here, AF plus BH, CE plus DG, and CF plus DH. So this describes at a high level an algorithm right away in 2 sentences. Here's how you say it. Take your input matrix, divide it into 4 matrices of size n over 2 by n over 2, then compute each of these products and sums of submatrices. That is the algorithm. That's the description. Let's define what the running time of this recursive algorithm would be. How many operations of size n over 2 by n over 2 are we going to do? I heard the number 8, right? Here's one of them. Here's 2. Here's 3, 4, 5, 6, 7, 8. So it's going to be 8 times t of n over 2. And then our algorithm requires the addition of several matrices. So we require 1, 2, 3, 4. 4 additions of n over 2 by n over 2 size matrices. And that is going to basically take 4n squared. Technically, it's n over 2 squared. Now take a look at that recurrence. What does it solve to? Which case of the master's theorem applies here? First case, right? Because this is A, this is B. So case 1 applies. And so the solution is going to be what? N to the log base 2 of 8, which is n cubed. Question? How did I figure out case 1 so fast? There are two reasons. First, I had you do exactly this thing 2 classes ago. When we were talking about the master's theorem, there was an example where this was 8t of n squared, and this was theta n squared right there. So we did this one before, and so you could have remembered that. Additionally, you just get an intuition for these things. You will have this intuition too. So this algorithm doesn't work for us, unfortunately. What is the problem? If I asked you to get an algorithm that's better than n cubed, what is going to be the driving problem of this type of approach? So from an asymptotic point of view, this 8 is the problem. This 8 with log 2, that's going to be the problem. You're never going to get rid of this n squared term here because the input is of size n squared. And the problem requires you to look at least all of the input. The problem here is you got to look at this 8 and you have to make it something smaller. So as you are doing your homework, when you come to a problem where we need to now get around this, you need to say, where is the problem? The bottleneck here is 8. So now you know what direction to look for. You need to find a way to do this type of recursion using less than 8 recursive methods like this. And so you'll think about it just like this guy did in 1960-something. He thought about it, and he came up with the following. This is really an algorithmic insight. This, by the way, there's a space problem here. This needs to be like that. So what he did, he looked at the same product that he needs, and he says, here's how I'm going to compute this product. First, in order to get this term, I'm going to add these two. So P1 and P2. These are the 7 multiplications that Strassen is going to need. The first one is P1, which is A times this term, and that is going to be. So notice by adding these two terms, he's able to get the term that he needs for this upper right matrix, AF plus BH. Similarly, in order to get this term, he's going to combine P3 and P4. And that, you will see, will also cancel out to get you the right terms. Here is where the real insight comes in. So in order to get this top term, he actually has to combine 4 of these. So if we take this term right here, P5, so let's go ahead and do the math for this right here. AE plus AH plus DE plus DH. Then he would add P4 to that, so he would also add, he will subtract DE and add DG. And then he'll subtract P2 from it, so minus AH and minus BH. And then he'll add P6 to that. So here we get plus BG minus DG plus BH minus DH. And now if we go through and cancel out all the terms, we end up with exactly what we want. So this formula works out. You can verify on your own that this formula works out as well. So let's get to the heart of it. What is the running time of Strassen's algorithm now? Notice, if we count the number of multiplications, we need 1, 2, 3, 4, 5, 6, 7. So this time it's 7t of n over 2 plus 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 plus 10. You're absolutely right. That's another flag on the play there. I forgot. So you do all of these operations, and then you add, so 10, 11, 12, 13, 14, 15, 16, 17, 18. 18. Good? This will also be case 1 of the master's theorem. And that's going to solve to log base 2 of 7. Okay? And that's roughly going to be n to the 2.805. Now, this was a magical discovery in the 1960s, early 70s. Nobody thought you could do matrix multiplication faster than the trivial n cubed one. This opened up a lot of ideas to say, well, there are many other things that could possibly be done here. So let's take this idea further. In 1975, this guy, Latterman, he found a way to use 23 matrix multiplications of size n over 3 by n over 3, plus a whole boatload of additions. Okay? So his algorithm would be 23 times t of n over 3 plus, again, theta of n squared. Quickly solve this. Somebody in the back. Good. So this is basically theta of n to the log base 3 of 23, which is n to the 2.854, right? Yeah, so this guy didn't make progress. This guy had 2.805, right? This guy had 2.854. So it's not a better algorithm, but he still published a paper on it. And the reason was people had published a paper. So by trivially, you can do this in 27 multiplications. If you think by 3 by 3, you can easily do it in 27. The reason he wrote a paper is someone wrote a paper that says, I can do it in 25. Then a really, really smart guy, a genius, said, I can do it in 24. This guy says, oh yeah, I got 23. Now, if you were able to get it to 21, if he had 21, then he would have something like this, right? Which would be, what is log base 3 of 21? You're not going to be able to do this in your head. This one is 2 to the, this is 2.79 something, right? 771, yeah. So 22 doesn't work, 21. If you found 21, boom, you've got, at that time, the world's best algorithm. So the reason that 23 was interesting was because this number is going down. 25, 27, 25, 24, 23. Could it be 22? Could it be 21? The other interesting thing about this paper, it's only a 2-page paper. You can Google it and find it and read it, and all of you can understand it. What's really cool about this paper is that he actually explains how he found this. It's too mind-boggling to think, oh, I just like took a nap and then woke up and had these 23 equations. It just worked out. He actually says, I've expressed this problem as a constraint problem, like this, and then I manually solved this using a systematic method. In other words, he was giving some algorithmic insight into how to come up with this type of thing. This guy, Victor Pan, actually took it to heart, because in 1978, he found a 70 by 70 matrixing in that much time. And let's do that multiplication. I know that it's a good one, so if someone has their calculator quickly, this would basically be T of n is equal to what is it? 795, yeah. So he actually beat Strassen. This guy actually beat Strassen using this extremely large matrix. And now here we go. This is 3. This is n to the 2.805, I think. This right here is the world record right now, which is somewhere around 2.36. For very large matrices, and for example, when you predict the weather, you're doing a finite element analysis on the entire planet to figure out where storms are going to move. Guess what you're doing? You're multiplying matrices that are super big. They're the size of the Earth down to 1 meter by 1 meter squares. You're using an algorithm that is one of these algorithms. Here's how this problem has moved. It was naive. They say 1950, but actually you might as well say 1950 BCE, okay? And then Strassen came up with his idea, Victor came up with his idea, and then there was a really big jump right here. This is using a slightly new idea. It's still divide and conquer, being a little bit relaxed, allowing certain mistakes to be made and certain approximations to be made and then fixed later on. There isn't much of an improvement. That line isn't going down much. But the point is, it was the last improvement. It's a new idea. Just like this right here was a new idea that eventually led to that. This is still an open question. We know it has to be more than 2 because you have to look at the input. But this is a kind of a crazy number, 2.36, da, 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 da. Why could it be like that? Why would the world have some crazy number like that? Seems like there's a better solution somewhere, right? Maybe one of you could figure this out. So now we come to the song's sake algorithm for this lecture, which is the fast Fourier transform. Why might you need the FFT? So I know that all of you are in an engineering school, and so many of you took a signals class. The FFT has more applications than just filtering or just analysis of electric circuits and so forth. For example, here's a stock price, stock chart. If you want to smooth that chart so that every one of these points is an average, a running average of 5 points, you could do that by going through the entire matrix and computing that window and that summation, or you could use the FFT to do that in faster time. Of course, there are these signal processing algorithms. So for example, when you take Shazam and slam it to the radio to figure out the awesome song that's playing, it is inherently doing an FFT to get a spectral analysis. And your cell phone, when it's encoding your voice to send electronically over the electromagnetic waves, it is also taking an FFT of your voice and then vocoding that into a compact representation. So your MP4 player, etc., all of these things are making use of this algorithm. What is the big idea in an FFT? The big idea is change of representation. You might have heard this as going from frequency domain to the time series domain. Electrical engineers think of it in this way. We're going to think of it as change of representation of a polynomial from coefficient form to pointwise form. And I'll explain what that means in a second. That is the one big idea. What does the FFT do? It changes representation. And this is a powerful idea because oftentimes a problem becomes easier by changing its representation to some other type of idea, doing some operations in that representation, and then changing it back. FFT is your first example in this class. The second big idea, it is a classic divide and conquer strategy. So it's yet another example of splitting the problem in half, doing both halves recursively, and combining them. Now, what did I say was the most challenging aspect of these algorithms is how to combine things properly. And in this setting, the FFT is going to be another example for you to think about how to combine the left and right halves. Let's look at a polynomial like this one. This is what we call the coefficient form of this polynomial. Because I'm defining the polynomial by giving you 5, 2, and 1. If I give you 3 coefficients, that uniquely determines a degree 2 polynomial. And you can move to the pointwise representation as well. So for example, we can compute f of 0, which is going to be 5, f of 1, which is going to be 8, and f of 2, which is going to be 13. So given a coefficient form, you can certainly go to point form. Because if I give you 3 points on a degree 2 polynomial, what can you do? So suppose I give you 3 points on a degree 2 polynomial. How do we recover a polynomial? How do we solve this problem? I give you 3 points, you find me the polynomial. 3 equations and 3 unknowns. So we know that f of 0 is negative 5. So we know that f of 0 is equal to negative 5, which is equal to 0, a times 0 plus b times 0 plus c. Okay? We know that f of 1, which is equal to, we know that f of 5 is equal to 30, a times 5 squared plus b times 5 plus c is equal to 30. And we know that f of 10, which is equal to 515, is equal to a times 1, 10 squared plus b times 10 plus c. So notice we have 3 equations, and we have 3 unknowns. So we can solve this. And of course, we can solve this using linear algebra, like matrix operations, like we just talked about. In particular, you would use Gaussian elimination, but turns out that almost all of the matrix operations, like Gaussian elimination, you can do with the matrix multiplication as well. I've just shown you that if you had the coefficient form, you could get to the point form. If you had the point form, you could get to the coefficient form. Now let's talk about the algorithmic question. We know that this is possible to go from one form to the other form. Now the question is, how much time does it take? How efficient is the transformation? So let's consider the brute force. You're given a polynomial in coefficient form like this. So obviously you can compute, like I did right there. You can take the numbers between 1 and n and just compute your polynomial. How much time would that take? If I were to just evaluate the polynomial at n points, how many operations would that require if I were to just do brute force? How much time would it take to evaluate a of 1? Order n operations, right? And so if I have to do that n times, it would take order n squared operations. In particular, you can just do this at the same time, right? You have x and you have a1, multiply a1 times x, and then, compute x squared. That's one multiplication multiplied by a squared. So each of these terms could basically take 2 operations. So that's how you do it. There's an even cleverer way called Horner's rule, Horner's method, which gives you a more elegant way of doing it too. When we see an algorithm that's order n squared, our instinct should be, can this be better? Just like as you entered computer science, you saw the bubble sort, and it was like, yes, that's n squared. It works. I like it. Can we do better? And we could. So here's the problem. We are given a polynomial in coefficient form, and we would like to change it into pointwise form. We don't actually care which points you evaluate this on, because we can go back and forth as long as they're different. The input is going to be a polynomial like this in coefficient form. So you just get a0, a1 up to an minus 1. And the output is going to be the evaluation of a on n distinct points. And they can be any n points. No restriction on which they are as long as they're different. By the way, the inverse FFT, if you're given n points and you want to move to coefficient form, it's same technique. So FFT and the inverse FFT are the same technique. We're going to learn about both of them. The algorithm for FFT is n log n. When I tell you an algorithm has to be n log n, you know right away that the solution has to be something like this. We are going to divide the problem into n over 2, into half. We're going to solve both of those halves, and then we're going to spend linear time to put them back together. Now the question is, when you're given a polynomial like this, how can you divide it into 2 parts so that you can solve them recursively? This is the algorithmic insight to this problem, and you got it within 10 seconds, so good job. The algorithmic insight is to rewrite a of x as a sum of the even parts and a sum of the odd parts. I'm just going to define a function called a even. Let's call it a even of y. And so that's going to be a0 plus a2y plus a4y squared plus a6y cubed plus dot 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 a to the n minus 2 over y to the n minus 2 over 2. And now I'm going to define an a odd, which is just going to be a1 plus a3y plus a5y squared plus a to the n minus 1 times y of n. Notice this is n minus 2 over 2, and this bottom exponent is also n minus 2. So this was the first insight. This was the second insight that we had. Check this out. We can write a of x as simply a even evaluated at x squared plus x times a odd evaluated at x squared. Right? So if we put in x squared into a even, we get a0, which is the same here, a2 times x squared, the same term right there, a4 times x to the fourth, dot, 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 a to the an minus 2 times x to the n minus 2. Similarly, if we plug in x squared to the odd powers, we'll get all of these, and then we add another x to get it right. So we get a1 plus a3 times x squared times x, so it's x cubed here. This will be x to the fifth, dot, dot, dot. This will be x to the n minus 1. Instead of splitting in the half, the idea was to split the odds and the evens. Now the point is, these two are both degree n minus 2 over 2 polynomials. They are polynomials that are half as big. We're almost there to a solution. Let me show you why this can be useful. Imagine that we already had the evaluation of AE and AO. We had recursively solved them. Like this, these are polynomials of degree roughly half. So they're of the same form. Now I have a polynomial of degree half, and I want to evaluate it on n over 2 different points. Let's imagine that we had evaluated them on 4, 9, 16, and 25. And similarly, odd had been 4, 9, 16, 25. I could compute A2 by basically looking at A04 plus 2 times A odd 4. This is true for any polynomial. A2 is equal to this even polynomial evaluated at x squared plus 2 times the odd polynomial at x squared. Similarly, I can compute A minus 2 at this point. So if we take that idea, given these four terms, given evaluations of AE and A0 on 4 points, we can compute A on 8 points. This is the new idea for merging. Instead of sorting lists or finding closest pairs or doing arbitrage or skylines or making bus routes, the way we're merging over here is by doing this algebraic computation. Given recursively having solved the odd and even, the FFT for the odd and even part of this, we can then compute the FFT on the full problem. So let's dig into this problem a little bit further. So the algorithm would basically be, let E be FFT on A even, let odd be FFT on A odd, okay? Comment, E is going to basically be, and then compute A of x is equal to, this is the basic FFT, and it's going to be n log n because each of these steps are recursive, and this step right here takes order n operations, right? Because it's just an addition and a multiplication. We look up these values, we look them up in this array. Now that is the algorithmic structure of this FFT. There's still one more complication that we have to overcome. The only mathematically complicated part of the FFT is coming up. Which points are we going to use? The example that I gave you had this very nice structure. The reason that 4 works, the reason that I could use 4 is because the square root of 4 is 2. This has an x squared and this is an x. For this type of thing to work, the points that we're going to have to choose just can't be arbitrary. The reason why my example worked here was because 4 has a square root, 9 has a square root, 16 has a square root, and 25 has a square root. Now we're going to need points if we want to do a dimension n FFT, we're going to have values that have n square roots. 4 has, like, when you take the square root of 4, you get 2. Then when you take the square root of 2, you get into a irrational number. So that's not going to work. We're going to need points that have n square roots. So we have to be very clever about the points that we use. We need numbers that have this type of solution. Give me one solution to this equation. 1. Give me another one. 0 is not a solution. Depending on n, let's say n is even, -1 works. What else? We are going to use complex numbers for this. But numbers are numbers. We shall not discriminate against the complex. So what are these roots? I'm going to recall this identity, this Euler identity. E to the 2 pi I is equal to 1. We're not going to prove that. We're just going to take that as a fact. But we're going to use it. E to the 2 pi I is equal to 1. That gives us a pretty good foothold on how to find the roots of unity. In particular, take a look at this list of numbers. You can write this again as just e to the 2 pi I, and then j over n, for j going from 0 up to n minus 1. Now, why are these roots of unity? Let's take e to the 2 pi I and do j over n, and let's raise that to the nth power. What do we get? We get e to the 2 pi I to the j, right? Because this n cancels with that n. But now, thanks to this identity, this is just equal to 1 to the j, and so we get 1. First of all of these numbers are unique. There are n of them, and they're all solutions to this equation. And furthermore, it's going to turn out that each of these has the requisite number of square roots. So the fourth idea in the FFT is you have to pick your points wisely. And you had to have the algorithmic insight to use these complex numbers. We're going to see exactly how this works. As for notation, I'm going to call e to the 2 pi I j over n. I'm going to call that omega j of n. It is the jth nth root of unity. The jth nth root of unity. How can I compute this number? It turns out that this is an identity. You can get this from the Taylor expansion. And on some Thursdays, I actually have enough time on this lecture to go through this, but this Thursday, we will not have. This Thursday, we're going to take this as a fact. And so now when you plug this in, e to the 2 pi I j over n, this is cosine of this number plus I times sine of this number. Now, all of you are familiar with sine and cosine. You've proved to me this fact on your handout there. And so all of you are capable of computing this first eighth root of unity. So let's do it. Omega 1 comma 8 is basically going to be cosine of 2 pi of 1 over 8 plus sine, I sine, so cosine 2 pi 1 over 8 plus I times sine of 2 pi 1 over 8. What does that equal? Use your sheet. Cosine of pi over 4 plus I times sine of pi over 4, which is basically 1 over square root of 2 plus I over square root of 2. That is our root. Let's draw them. What I was going to do on this slide right here is draw all of these roots of unity. That if we actually computed omega of 0 comma 8, that's going to be 1, because cosine of 0 is 1, and sine of 0 is 0. So this is omega 0, 8. We just computed omega 1 of 8. This is the imaginary plane, by the way. This over here is I, right? This over here is what you know. This is going to be omega 2 of 8, 3, 4, 5, 6, 7. The roots of unity, you can picture them on a circle in the complex plane. And they basically divide the entire circle into equal number of parts. And why did we need to pick the roots of unity? The fact I'm going to show you now is that when you square each of the roots of unity, if you square the nth roots of unity, you get the n over 2th roots of unity. And this is going to be the property that we need in order to plug these points in to the FFT algorithm. That's all the FFT is. Plugging in this set of numbers, the roots of unity, into that divide and conquer algorithm, which you're familiar with, right? That structure is easy. Half, half combined with that linear equation. So all that remains is for me to show you that when you square each of these points, you get the 4th roots of unity. So these are the 8th roots of unity, the red points. And now take this number right there. That's 1. If we square it, we get 1. Okay? This right here, if you remember, was 1 over square root of 2 plus I over square root of 2. And if we square it, we basically get 1/2. So 1/2, and then this is I over 2 times I over 2, right? And then this is going to be I squared over 2. So this is 1/2 plus I minus 1/2. The point is, when you take each of these points, squaring this is kind of like rotating it another 50 degrees, another 45 degrees. So if you square this value, you come to right over here. If you square this top value, which is I, you come to -1, which would be right here, right? I squared is -1. If you square this value, you're basically going to move, you move 3 over here, you'd move 3 over here, okay? If you square this value, you come back to this. If you square -1, you come back to 1. And if you do the same sort of things here, you end up at each of these same 4 points. There's a proof. It's easier to prove this type of thing. But the main point is that these, if you square the nth roots, you get the n over 2th roots. We'll finish the FFT and then finish median on Tuesday. Have a good weekend, everyone.